His professional and academic career has been carved out by his dedication to transportation engineering, and since 2017, he has played a pivotal role in developing ITS policy of Japanese government. His presentation is titled as Ongoing Development of Cooperative Intelligence Transportation System ITS in Japan. Mr. Mawatari, floor is yours.
Thank you for your introduction, Mr. Kikukawa. Good afternoon, everyone. I'd like to thank you for giving me a chance to speak here today regarding cooperative ITS, which means Intelligent Transportation Systems. Let me just start it by introducing myself. I'm S.MAWATARI, and the Senior Deputy Director of the ITS Policy and Program Office in the Road Bureau within the Japanese Ministry of Land, Infrastructure, Transport, and Tourism. As you can see on the screen, today I'd like to talk about recent efforts to develop cooperative ITS in Japan from the perspective of road administrators. Today's topic is particularly relevant to those who are interested in cooperative ITS, especially using vehicle probe data to solve the various problems. I will discuss two major topics today, and first, I will give an overview of ITS deployment in Japan up to now. After that, I will discuss the latest system named ETC 2.0. This is the world's first cooperative system deployed nationwide with a variety of applications. At the very end, I will discuss future approaches to cooperative ITS, especially utilizing probe data. In Japan, road transport faces many issues that must be resolved, such as traffic accidents, congestion, and environmental degradation. We have still 470,000 traffic accidents in 3,700 fatalities, and lost about 40 hours per year person by traffic congestion. ITS uses information and communication technologies to connect people, vehicles, and roads. It is one of the most important tools we can use to resolve these issues. ITS has been introduced in a broad range of fields in Japan. First of all, I will talk about the deployment of ITS in Japan. Since the 1990s, various systems have been introduced. The use of car navigation systems became widespread. This was followed by the introduction of the Vehicle Information and Communication System, or VICS, a system that provides information on traffic congestion. And electronic toll collection, or ETC, a system for automatic toll collection on expressways, was also introduced. In 2011, IT Spot Service, which integrates all of these basic technologies, was introduced. IT Spot Service was the world's first road vehicle cooperative system. The concept was to provide various applications using a single vehicle onboard unit. In 2015, ETC 2.0, a further evolution of this service, was introduced. This service uses probe data obtained from vehicle to achieve advanced applications. I will discuss this service in greater detail in a moment. I'd like to emphasize that cooperation and joint activities by the government and private sector companies are indispensable for promoting and ensuring widespread use of ITS. In Japan, the government formulates standards and specifications, and private sector companies conduct technical development and sales promotion activities on their own. Through this type of role sharing, the country as a whole works to disseminate ITS. At present, onboard units have been installed in tens of millions of vehicles. Let me explain the benefits using ETC as an example. Expressways in Japan are toll roads. Tolls are assessed by confirming when a vehicle passes through the expressway entrance and exit. With ETC, the vehicle simply passes through the toll gate without stopping. The roadside sensor installed at the toll gate and the onboard unit in the vehicle communicate with another, and the toll is charged to the driver's credit card. Currently, 90% of the vehicles traveling on expressways in Japan are equipped with onboard units. This has almost eliminated congestion at toll gates, which used to occur for 30% of the total congestion on expressways. Excuse me, sorry. Next, I'd like to talk about ETC 2.0, the world's first driving support service using a road vehicle cooperative system. ETC 2.0 is a system that enables various types of information to be provided to drivers and enables road administrators to receive vehicle driving information and route information, in addition to the ETC function, through high-speed, large-capacity, two-way communication between roadside sensor and a special onboard unit. The basic information provided to the drivers includes congestion information over a wide area. Previously, it was only possible to obtain congestion information over short distance using the VIX system that I have described. But ETC 2.0 distributes wide area congestion information so drivers can drive smarter by selecting routes that are not congested. And real-time images are distributed to support safe driving. As shown in the slide, drivers are cautioned by providing cautions against rear-end collisions when there is congestion ahead of a curve, or by providing information on snowy road surface conditions or congestion conditions on the road ahead in real time. The service is now its 5th year. Roadside units have been installed at about 3,600 locations throughout the country, and onboard units have been installed in more than 2.4 million vehicles. So use of the service is advanced in all locations throughout the country. What I'd like to emphasize to everyone today is that the major feature of the ETC 2.0 system is that vehicle driving information and road information is collected by road administrators. In other words, probe data that includes information on vehicle speeds, accelerations, and position is collected and utilized in various ways. As I explained previously, information on vehicle positions and acceleration is collected by roadside units installed throughout the country using communication between the road and the vehicle. In this operation, thorough care is given to how personal information is handled. The data is compiled into the road administrator's database and accumulated as information on speeds, driving routes, and sudden braking of each vehicle. This accumulated data is utilized by the road administrator for identifying various issues regarding the road, such as relieving traffic congestion, reducing traffic accidents, and analyzing measures to deal with these issues. I will describe various examples of measures against congestion measures against traffic accidents, support for disaster recovery, and support for logistics. I'd like to explain some examples. The probe data collected by ETC 2.0 are primarily used to improve the efficiency of road investment. I have already explained to you that congestion at the toll booth, which was responsible for about 30% of the expressway congestion, has been virtually resolved by the introduction of ETC. However, there is still considerable congestion on expressways. Therefore, initiatives are in progress to pinpoint countermeasures against congestion by scientifically analyzing the data to identify the causes and locations where congestion occurs. In this example, an analysis of traffic capacity that ensures a smooth flow of traffic was conducted based on speed data for each road sector and time period, and road gradient data. The analysis identified sectors in which the actual traffic volume was reduced by points where the road gradient changed and ascending slopes. These sectors are shown in red in the slide. Based on the results, the number of lanes was increased from 2 lanes to 3 lanes in these sectors. This made it possible to efficiently eliminate congestion at a low cost. And this slide shows an example of the use of probe data for traffic safety measures. Traffic accidents on main roads in Japan have been decreasing, but there has been no reduction in the number of traffic accidents that occur on residential roads. There are many accidents involving elderly pedestrians in particular, and devising measures to prevent such accidents is an urgent problem. For this reason, while naturally it is important to devise measures after an accident on a residential road has occurred, we also need to devise measures in advance for locations where there is a potential danger of accidents occurring. In the map shown in the left-hand portion of this slide, the red X indicate places where drivers braked suddenly, as determined by an analysis of the acceleration data included in probe data. The current status of these locations was checked based on the data. The check revealed that the causes of the accidents were, for example, that vehicles were driving too fast on the narrow road, or that roadside trees had grown to the point where visibility was poor. Based on the results, effective measures can be implemented for these potentially dangerous locations, such as providing speed bumps to get drivers to reduce their speed, improving visibility, and so on. Currently, such activities are underway at more than 400 locations nationwide as a joint effort on the part of the local governments, local residents, and school personnel. Next, this slide shows using probe data for recovery from natural disasters. Japan is subject to frequent earthquakes, torrential rains, and other disasters. In the aftermath of a major earthquake or other disaster, a great deal of time is needed to identify possible routes. For this reason, the driving records of individual vehicles are used to determine routes that are likely to be impassable because of roads and bridges that were damaged by the disaster. This blue line on the map indicates travel records in 24 hours after the earthquakes, which occurred in 2016. We could identify this area was damaged because there was no travel record. The ability to quickly confirm passable or non-passable routes and share this information with the relevant authorities helps to save lives and ensure the delivery of emergency supplies. And ETC 2.0 data are also used to improve logistics productivity. In Japan, low birth rates and aging is progressing together with population reduction. In particular, in recent years, there is a significant problem of insufficient numbers and aging of truck drivers as a result of a small road transport. To deal with this, an experiment is being carried out in which the data on positional information of logistics trucks collected by road administrators using ETC 2.0 is returned to logistics companies that have agreed to participate. By this mechanism, the logistics companies can determine in real time the position of their vehicles, enabling them to efficiently manage the operation of their trucks and deal with insufficient numbers of drivers. Also, information on sudden acceleration and sudden deceleration of logistics truck is returned to participating logistics companies. In this way, the logistics companies can determine dangerous driving characteristics of drivers, such as sudden acceleration and sudden braking, and this can be utilized in safe driving education for drivers. This experiment has been going on for about 2 years now, and it has been positively evaluated by the logistics companies using it, who have expressed the opinion that they would like to continue using it in the future. Therefore, introduction of the system in earnest and expanding the range of target vehicle is being considered from this year. And cooperative ITS technologies will undoubtedly be needed to support automated driving as well. At present, it is not possible for a self-driving vehicle to recognize all of the complex traffic conditions in its surroundings using only its sensors. Roadside units can determine the traffic status, such as volume of traffic and the traveling speed on the main expressway, and this information can be provided to self-driving vehicles that are about to merge onto the expressway. This will help ensure smooth merging onto the expressway. Also, as another example, consider the case where vehicles that have been involved in a traffic accident and goods that have fallen onto the road can only be spotted when they are immediately in front of a self-driving vehicle. And there is no scope for automatically changing lane. In this case, also by providing the appropriate information to the self-driving vehicle in advance, it is possible to achieve a smooth lane change. This year, we have just begun joint research on this type of service, working with automobile companies and equipment manufacturers. We want to further research cooperative ITS technologies in order to realize a safe and smooth automated driving society. Finally, let me talk about 3 activities that will be needed from this point on regarding cooperative ITS, especially utilizing probe data. First, regarding the ETC 2.0 service of providing information, we want to provide information that is more in line with the driver's needs. This will result in increasing the spread of onboard units and the collection of more data at various locations throughout the country, which has greater advantages for road administrators. Second, as I've mentioned before, Japan is facing a decrease in population. Therefore, it is necessary to promote initiatives to achieve a more productive society by supporting smarter investment and logistics, utilizing the data collected by ETC 2.0. Lastly, an enormous quantity of data is collected by ETC 2.0. Therefore, in order to solve the problems of society by effective utilization of this data, it is considered necessary that this data be utilized not only by road administrators, but it is also necessary to examine mechanism for wider utilization and mechanism for making this data more open, while understanding the needs of industry and academia. And today, I have described how cooperative ITS has been developed in Japan and current initiatives being undertaken. ITS is an important tool for resolving various road-related issues. During the past 20 years, ITS-related efforts have produced significant achievements. And a major technical revolution is unfolding, such as the spread of automated driving and the accumulation of big data. So in the future, we see that Japanese cooperative ITS will also enter a new era. We plan to continue working to advance ITS in Japan even further. And this concludes my presentation. Thank you so much for your attention.
Thank you very much, Mr. Mawatari. And does anyone has any question or comment? Okay. The microphone is coming. Please wait.
Does the performance of the ETC system depend upon the road condition at all? For example, does the ETC system need clear lane lines or clear striping or a lack of potholes? Does that affect the performance?
I'd like to confirm what your question is asking, ETC 2.0's performance. So, right? Sorry. Could you repeat your question again? Sorry.
So the question is, does the performance of the ETC system depend upon the condition of the road? For example, will the ETC system perform better on a road in good condition where it has good lane lines and a lack of potholes, or does it not matter to the ETC system?
Thank you for your question. Currently, this system can't detect the condition of the road.
Okay.
Just to know the speed of the vehicles or acceleration of the and the locations.
Thank you.
Yes.
Thank you very much. So, what the benefits for the car user to have this system in their cars?
Pardon? Sorry. Could you repeat your question?
Yeah, the car, you install the device for system in the cars. What's the benefits for the users, the users' cars?
Firstly, drivers can receive various information. I explained earlier. Drivers can receive wide area congestion information, and they can receive a real-time image of the road, like snowy conditions or congested condition. That is, I think that is a benefit for drivers. Is that answer for your question?
The user cars users, they accept to install a device in their cars.
Yes, drivers accept using this data. Yeah.
Any other comment or question? Okay.
Yes. You've mentioned the issue of privacy, which is very important. So we mentioned that the road operator is aggregating the data in order not to have private information inside. But how can you avoid that third parties take the information in the air and use them for other purposes without that aggregation? How is there a way to avoid such interception of the data?
We don't collect the personal information like number plate or driver's name. So, and we can't collect the data from the near. Restriction will also be placed on timing of data, meaning when it begins and ends, to ensure that departure locations and arrival locations are not identified. So we can use this data more open. Thank you.
Thank you very much. Then I'm going to move to the second speaker, okay? Okay, second, thank you very much, Mr.
Thank you very much.
Mawatari. Okay.